Now let's consider where are the electrons around an atom. The basic answer is we don't know where they are. But we can say is we have a probability, we can calculate the probability of finding an electron in a certain region of space that we're interested in. That's all we can say. We don't know where it is. We can only determine, say, there might be a 20% probability of finding the electron in a certain region around the nucleus, but we don't know anything else. It's energy, angular momentum, but we don't know where it is. So this is the big difference in quantum mechanics and classical mechanics. Classical mechanics has precise trajectories. We can throw a baseball. If we know the forces on the baseball, we can calculate exactly where it's going to be at any time. For subatomic particles, we don't know where they are. We can only calculate probabilities of them passing through or being in a certain region of space. As a consequence of their wave-particle duality. Regions of space that electrons occupy are called orbitals. We can assign orbitals to the different combinations of quantum numbers. Say we have the 1s0 energy state. We call that a 1s orbital. Say we have a 2p1 energy state. We call that a 2p orbital. Orbitals have various shapes. S orbitals are spherical in nature. So we'll draw a sphere here. So that would be like a 1s orbital. And what that sphere represents is the diameter of the sphere would represent a probability of an electron. So we might draw the sphere so that 70% of the time the electron is within that sphere. The other 30% it's outside of the sphere. So just depending on what probability we want to pick as to how big or little the orbital is in our drawing. So s orbitals are spherical. So if we have a 2p orbital and we plotted them, and we can only plot part of the orbital at a time because they depend upon 3 spatial dimensions, and we need an extra spatial dimension to plot anything. So if we have 3 spatial dimensions, we would need 4D space to plot them. But we can plot 2 of the spatial dimensions at a time. So we could plot the p orbital, and we would find that the radial distribution, the distance from the nucleus of the atom, would look like this for a certain probability. Say this might be 70% probability of finding an electron in this region of space. You'll notice a couple of things. There are 2 lobes, and there in the middle is called a node, and the node just means that there's 0% probability of the electron being there. So we have a point in space, this node, at which there's 0 probability of the electron being present. The electron can be in this top node, or the electron can be in the bottom node. But you might ask, how does it get from the top to the bottom if it can't exist in between the nodes? Well, this is the thing about quantum mechanics. The electron exists in both places at the same time. If we detect it, it will collapse into a smaller region of space, like particle nature, but when we looking for it, it will diffuse out, and its wave nature will take over, and it will exist in both nodes simultaneously. The peculiar nature of subatomic particles. Now let's see how these shapes correspond with quantum numbers. Say we have the 1s orbital, we have a sphere. There's only a single way that the quantum numbers can be arranged for the n equal 1 level. N equal 1, L equals 0, M sub L equals 0. Now say we have a 2p orbital. So in this case, we've seen that it looks like two lobes separated by a node. N equals 2, L equals 1, M sub L can be 0, -1, or 1. So actually there are three separate p orbitals. One can exist along, say, the z-axis, one along the x-axis, y-axis, and the other along the x-axis. So I've drawn this dotted showing the lobe goes back away from us. So these are the three different 2p orbitals. And because there are three separate M sub L values. Now if we had, say, a 3d orbital, there are 5 M sub L values. M sub L can be -2, -1, 0, 1, or 2. So there are 5 separate M sub L values. So there are 5 separate 3d orbitals. There's 3d2, 3d1, 3d0, 3d -1, 3d -2.